Even though, okay, there's still people coming in.
I can start slowly.
Yeah, just start. Yeah, shall we start?
Yeah, sure.
Okay, so welcome everyone. So Niels asked me to introduce today's speaker. Welcome to this PrimaVera talk by Professor Frits Vaandrager from Radboud University Nijmegen on finding software bugs using active automata learning. So Frits, if you're ready, the floor is yours.
Yeah, I'm ready.
Okay, perfect.
Yeah, so this talk may not be directly related to predictive maintenance, but Marielle suggested that it might be interesting for this audience because of the focus on state machines, which play a pervasive role in many systems, but also the focus on both active and passive learning. And anyway, it's a fun topic, at least that's what I think it is, and so I enjoy telling you about it. So I will give a very slow introduction, a brief introduction to model learning. Then I will focus on applications. I will just tell you about all the case studies we've been doing. I have a few slides sort of explaining on theory and tools that we're using and current research topics, and then conclude and future work. There's lots of future work. So, okay, state machines. Maybe you're not all that familiar with state machines. With my background in automata theory, I see them everywhere. So whenever you have some system, then typically it has a couple of modes, and due to inputs, buttons that you press, or maybe due to action by the system itself, it changes from one mode to another. And so we can describe our coffee machine and our microwave using state machines, but we may even describe our own behavior by identifying a few modes and the triggers that bring us from one mode to another. And definitely embedded systems, computer-based systems, software can be often described in terms of state machines, and this is very insightful. It is useful to understand in what modes a system can be. So the topic of my research is to figure out for a given system under test, an SUT, what is the state machine that is governing its behavior. And so I do this by sending inputs to the system and observing the resulting outputs, and then trying to come up with state machines. So for those of you who are familiar with control theory, this activity is called system identification in control theory. So I do system identification, but then my goal is to learn automata. Now, in order to be able to construct an automaton, I need to make some assumptions, and typical assumptions that we make, but actually most of them are not necessary, but they're really useful, is that it's always possible to bring the system back to the initial state and start a new experiment, because this allows us to explore all the possible behaviors by bringing the system back to its initial state, and then again offering some inputs. We also typically assume that systems are deterministic. So if we provide the same sequence of inputs twice, we will end up in the same state and observe also the same outputs. So these are strong assumptions, and of course in practice sometimes this is tricky. You cannot fully reset a machine. Maybe the machine is not entirely deterministic. But for many applications this is the case, and that helps a lot when you want to construct models. So this activity of constructing models, people mostly, you can view it as a special kind of machine learning. And machine learning, of course, is very popular these days. So how can we see this? Well, in machine learning, typically the objective is that you are given a finite number of samples, data samples, and then you want to find some function which sort of explains all these data symbol, all these samples, so that when you're given a new x, you can actually sort of predict the corresponding y, which is generated by this function. So you want to learn, they are either cats or dogs or what is it? And then your task again is to come up with sort of a general function which for arbitrary pictures is able to do this classification. So how can we view state machine learning in this setting? Well, let's consider a special case of finite automata. And so here's an example of a finite automaton. We have a couple of states and an input, which can either be a 0 or a 1, brings us from one state to the next. We have an initial state, which is S0, and there's also an accepting state indicated by a little circle, which in this case, in this example, also happens to be S0. So a word is a sequence of symbols, input symbols, and a word is accepted if when you start in the initial state, you get to an accepting state. So in this case, for instance, the word 1, 1 is accepted, or the word 1, 0, 0, 1. And actually, so this simple automaton accepts all the binary numbers that are multiples of 3. So this is an infinite set of words, and so we can play this game of machine learning. So we can consider the task where you are presented with a finite number of words, and then the task is to come up with an automaton like this. So that is a classical problem in computer science. We are given a language L, and elements of L are finite sequences over some alphabet sigma, so they're finite words. And each word is either in the language or not. So we can represent this language by a characteristic function, a function which labels any word as either belonging to the language, 1, or not belonging to the language. And so what we want to compute is sort of a finite representation of this function, and an automaton is such a representation. This is an old problem, and already in 1956, Edward Moore had a very nice paper, Gedanken Experiments on Sequential Machines, where he addressed this problem. And well, there's been some follow-up work, but this is a classical problem. So let's discuss a bit how this works. And maybe this slide is a bit technical, but subsequent slides, I think, will explain these ideas. So given two words, we say they are equivalent for a given language L. Yeah, basically after doing either U or V, you end in the same state of the automaton. That is, no matter what happens afterwards, what subsequent sequence of symbols W occurs, if UW is in the language, then VW will be in the language, and the other way around. So two words are equivalent if you cannot distinguish them by adding any suffix. And distinguish means that you come to an accepting state or a non-accepting state. And there is a well-known theorem by Mealy and Herold, which says that a language can be accepted by a finite automaton if and only if this equivalence has finitely many equivalence classes. Well, so this may be a bit technical, but let me try to convey the intuition by some simple pictures. And so let us consider a simple language. And so this is described by this expression, which is called a regular expression. And basically it corresponds to all the words over the alphabet AB, which begin with an A. Then there is a finite sequence consisting of B's and A's, can be any symbol, and then there is a B. So these are the words over alphabet AB that begin with an A and end with a B. So what we can consider is a table where in the rows we have a row for every sort of finite word, and we have a column for every finite word. There's here also the empty sequence denoted by this bar, and then we start filling this table, and we write a 0 when the concatenation of this word AA in the row with the corresponding symbol in the column is a word in the language. And AA is not in the language because it doesn't end with a B, so we write a 0 here. But for instance, AAB is in the language, so in this entry of the matrix we write a 1, and so on. So BA is not in the language, and actually whatever we append to BA, it is not going to be in the language because BA doesn't start with A, and that we need for a word to be in the language. So this basically is an infinite matrix because we have a row for every word over the alphabet, and we have a column for every row of the alphabet. So there are infinitely many rows and infinitely many columns, and the matrix is filled with 0 or 1s depending on whether the concatenation of these two is in the language. So now we can observe that AA and BA sort of have a different row in the matrix. If we look at all the 0s and 1s, that's different for AA and for BA. And that is intuitively because we end up in different states. If we do BA, then we know we cannot have an accepting word in the language, whereas in the case of AA, that is possible. So AA and BA are not equivalent in the Nerode sense, because there is a suffix, in this case it is B, for instance, which distinguishes these two words. Okay, and so what we can do with this infinite matrix is sort of try to figure out what different types of rows we have. And then we see many symbols which have the same row as A, many words, those are yellow, many which have the same row as B. In fact, there are still 2 other possible. Altogether, there are 4 rows in this Hankel matrix. So that indicates that we can build a state machine which accepts this language, which has 4 different states. And so to summarize, we say that 2 words are Nerode equivalent if and only if the rows for these words in the matrix have the same color. And that means whenever some suffix W has the property that UW is in the language, then VW will also be in the language and vice versa. And the language is called regular if this infinite matrix only has a finite number of distinct rows, which we represent using colors. And the number of states in the DFA for the language actually equals the number of colors in the Hankel matrix. So if I give you an infinite matrix, I don't know how to give you an infinite matrix, but okay, here you see a fragment of it, a finite fragment. Then the question is, okay, how can we construct an FSM? And that's actually a pretty straightforward procedure. Because what you do is first you color the rows, You identify what different rows you may have. In this case, you see 3 different colors, and then you construct an automaton. And in order to construct an automaton, actually you need just a small fraction part of the Henkel matrix. We only need the first column, and we only need to have 1 row of each color plus all the extensions with a single symbol. Why is that? Well, the states are going to be the colors. So there are going to be 3 states: yellow, gray, and orange. And whether a state is accepting depends on whether this word is in the language. If it's in the language, it should be accepting. So that means that the word concatenated with the empty word, that is the word itself, is in the language. So here we can see that the yellow state must be accepting, the gray state must be accepting, and the orange state is not accepting. And then if you want to know the transitions in the automaton, we just look at the extensions of the basic 3 words with a single symbol. So if we are in the yellow state, corresponding to the empty sequence, and we do an A, well, then we jump to this equivalence class, that is the orange class. If we have a B, then we jump to the B state. But if we are in the A state and we do another A, we jump to the state AA, which happens to be yellow, and so there is a transition back to the initial state. Okay, so in this way we can construct an automaton, and this is a very general construction. Now, in practice, we don't, of course, have infinite matrices. So in practice, when we observe some system, it can be a microwave or coffee machine or some piece of software, we of course can record traces, we can record sequences of inputs and outputs, but at the end we only will have a finite number of traces. And so given those traces, what we can try to do is to fill at least part of the Henkel matrix, and we will always be able to only fill an initial part of this matrix. And so we will see some 1s and some 0s occurring in the matrix. And then things become harder, because then if we want to figure out the colors, that's not so clear. For instance, it's clear that ABAA must be in a different, lead to a different state than ABA, because there's a 0 and there is a 1. But is ABAA equivalent to A? Well, it might be. Sorry, is it equivalent to B? Yeah, that might be, because both we have 0s here. But in general, to figure out the minimal number of colors that is needed to color this matrix, that is an NP-hard problem. That's really difficult computationally. So there are algorithms and there are tools which do it. So given a finite number of words, you construct an automaton. And in the Netherlands, we have Sikko Verwer from the University of Delft, who is really a specialist in those type of tools, and he has state-of-the-art tools which sort of tackle this NP-hard problem and try to come up with state machines given a finite number of traces. But in my research, I have been following a different avenue. So I'm looking at active learning. So the idea is that we actively try to fill the relevant parts of the Henkel matrix to come up with an interesting state machine which explains the observations. So rather than just passively waiting for whatever observations the system is willing to give us, we become active and we ask queries. So Angluin considers a setting where you have a learner and a teacher. and the teacher sort of knows an automaton, and the learner can pose questions. So the learner can send a string to the teacher and ask, okay, is this word in the language? And then the teacher answers either yes or no, depending on whether the word is in the language. And after a number of queries of this form, the learner may construct an hypothesis. That is, she may construct an automaton which is consistent with all the observations made thus far. It's consistent with all the membership queries. But it still need not be correct, right? Because maybe there are more states than the learner could distinguish because she has not seen certain very long words. But what the learner can do is to send this automaton to the teacher, who is then so kind to give an answer whether this hypothesis is correct, whether the language accepted by the automaton is the same as the language accepted by the automaton which she uses as a basis for answering queries. And so either you get an answer yes or no, and if the automata are different, you get a counterexample. The word is in which is accepted by one automaton but not the other. So this is a very nice conceptual game, and Taint Angluin came up with a algorithm where you just need to ask a polynomial number of queries, and then a learner can learn the automaton. And so basically what happens in Angluin's algorithm is that the learner tries to sort of complete a part of the Hankel matrix. So maybe at some point she has identified a number of different states, states where depending on the suffix, either you end up in accepting or non-accepting, and there are differences in the patterns here. And then you try to figure out what happens if you do one more symbol, because that will allow you to figure out how the transitions go. Now, if you end up with a different row in the matrix, you have discovered a new state. But if not, then at some point things converge and you will come up with an hypothesis. And then given a counterexample, typically you need to add some additional rows or columns to the matrix, so the matrix will grow. But eventually, and that's proven by Angluin, you learn a minimal automaton. Okay, so this is nice, but is it useful? So how could we use this to learn software? So this leads us to work by Peled, Vardi, and Yannakakis, a very influential paper which is called black box checking. So they observe the following. They say, okay, membership queries typically correspond to traces of some real piece of software. So suppose we have a system under learning, then if we send certain inputs, then we get certain outputs, and basically that gives us words which are in the language. So that we can do. The tricky thing, of course, is the equivalence oracle, because if we learn a model from software, then we cannot give a state machine to the software and ask the software whether this actually accurately describes its behavior. That's not how it works. However, what we can do is we can resort to a mature field in computer science, which is called conformance testing, where people studied algorithms which, given a finite state machine, check whether a piece of software conforms and behaves the same. So Yannakakis has been a leader in this field. And basically what you do is you sort of send lots of tests to the system under test. You do this in a smart way. And whenever you see a discrepancy between the traces that are allowed by the hypothesis and the behavior of the real system, you have discovered a flaw. And there are really smart algorithms for doing that. So what Peled, Vardi, and Yannakakis propose is to use a conformance testing tool here. And now conformance testing tools are not perfect equivalence oracles, because at some point If you have been testing for 3 days in a row, you may conclude that you see no bugs. The implementation appears to be correct. But then it could be that right after that, there would have been a counterexample showing a discrepancy. So we approximate the perfect equivalence oracle of Angluin, but still this is a useful way of doing active learning. And so this is the approach we have been applying in my group and trying to push further. So we collaborate with a team from the University of Dortmund, of the group of Professor Steffen, and they have a mature tool called LearnLib, which supports learning of DFAs and variations of different types of state machines, Mealy machines. And so we've been using and extending this tool. So our approach is really to sort of do case studies, try to improve the tools, try to develop new theory, use the improved tools to do more challenging case studies and so on. Now in practice, the learning tools have some limitations. So typically they can deal with, say, 20 input symbols. But if you have a real piece of software, like say the TCP protocol, or then typically there will be a limited number of method calls or procedures or events, but these are parameterized by data values. So there are basically lots of different input messages that you can typically send to a piece of software. And if there are a few hundred input symbols, then the learning tools simply don't scale, because the table that you have to construct, this part of the Henkel matrix, is going to be too big. And so something we apply in practice there is that we have an intermediate component between the learning tool, which can only deal with a small set of symbols, and the actual implementation, the teacher in the Angluin terminology, which accepts maybe millions of different inputs. And basically the idea is to abstract. So for instance, if you enter your password, well, there are maybe 100,000 different passwords which you could select, but at an abstract level, either your password is correct or it's incorrect. And so often for learning purposes, this is you can come up with some abstraction which turns a big state machine into a small state machine that you can learn, and then still having this abstract model gives you a lot of information about the behavior of the system. Okay, I described already, this is our research method. We have this interaction of theory, tools, and applications. And I think what's really nice about active automata learning is that this sort of machinery works. And we have some very powerful applications, and that helped us to come up with nice new theory. So here are some examples. So one of my PhD students looked at the EMV protocol. So that is a protocol which is running on each smart card that you have in your pocket. It's supported by, it has been developed by Europay, MasterCard, and Visa. And so we have built a setup where we interact with some smart cards. My student had a whole pack of smart cards, and then you try to learn how this card interacts with the card reader. And the interaction is described in a standard document of more than 700 pages. But using 1,500 membership queries, 1,500 tests, and that took us less than half an hour, we were able to generate this small state machine. And people familiar with EMV recognize this state machine, and it provides a compact representation of many pages in the standard. And the interesting thing is that different cards have different state machines. So depending on the manufacturer, the bank, and so on, you get slightly different state machines. And so we can use this for fingerprinting. Another example is the identifier, which is a device used by ABN AMRO for internet banking. And one of our students at some point discovered a security bug in the identifier. If it was communicating via laptop using USB, something was not implemented correctly. And we were able to actually reproduce this bug using model learning. So we managed to learn one state machine for the old identifier and a different one for the new corrected identifier. And so even though this actual bug was not discovered using automata learning, we would have been able to do it if the student would have used the technique right from the beginning. So then in my group we looked at many protocols, and basically the situation is as follows. If you take any protocol, any major protocol, then it takes a while to learn a model, but then any implementation contains at least some standard violations. So there are some transitions in the state machine which are not supposed to be there. And very often these are sort of details, and people don't really care, but sometimes there are major issues which are being fixed. And so I think this shows a standard violation in the Windows implementation of TCP, and that never has been fixed, and we never got a reaction actually. But we also found some standard violations in the Linux implementation of TCP, and those have been fixed. So that's a nice idea that active learning helped to change the Linux implementation. So here you see another example, the SSH protocol. So this is the state machine that we learned, and then typically in all these protocols there is sort of a happy flow, sort of the regular behavior which you follow during a normal run of the protocol. And then there is the weird behavior, the things that happen when unexpected inputs arrive at unexpected moments. And of course, these are exactly the type of behaviors that hackers try. Yeah? They try to press strange buttons at strange moments. They try to send weird inputs. And so it's really important how the protocol behaves when these weird input occurs. And there we see lots of differences between implementations, and often implementers make mistakes. And so in this specific case, some of the red transitions correspond to mistakes. So it's interesting how we sort of discover these flaws. And so if the state machine is wrong, then someone who understands the standard and understands the protocol can look at the state machine and say, well, yeah, I think this transition shouldn't be there. But yeah, if you have lots of different implementations and the state machines get more complicated, then you need to mechanize. And so what we use is a technique called model checking, where correctness properties of these protocols are being formalized using temporal logic. And we have a tool called the model checker, which automatically explores whether for a given model the property holds. And so here you see, for example, that for the SSH protocol, we stated a number of properties, and we looked at 3 different implementations, and here we indicate which properties are valid or not. And sometimes, I think with the X star, you can debate whether we formalize the thing correctly or whether there's really a standard violation. The standards are written in natural language, so it's always tricky to prove that you have a standard violation, but in the X cases, we really have found issues. And so what's also interesting with this model checking is that, so if we've learned a model and we apply model checker and we discover that some property doesn't hold, then we always need to reproduce the counterexample, which shows that a property doesn't hold in the real system. Because it could be that our model is incorrect and the real system is correct. So sometimes when we find that a property doesn't hold, the conclusion is that our model is incorrect, but then the model learning tool gives us a counterexample and we can improve our model. So that's actually quite useful. So we have, within my group and also in some other groups, have applied this to numerous case studies, and I think by now it's becoming pretty routine. So when for a while we had the idea, okay, if there is a new bachelor student, we just give him or her a protocol. We give an introductory tutorial on model learning, and then 2 months later we have a bug in an implementation. We try to speed this up. So 2 years ago we organized a workshop in the Lorentz Center in Leiden, and there we brought together specialists on protocols and specialists on automata learning, and they're typically if these people were sitting together, within 2 days or so, they were able to already learn some first models, and so several papers have come out of this workshop finding bugs and suggesting improvements for protocol implementations. So this is really getting pretty routine. More challenging, I think, is to apply this stuff to real industrial software, and so we've been working on this with some success. So for instance, we have been collaborating with OC in an effort to learn a state machine model of a realistic printer controller. So OC is now called Canon, but this printer controller is used in virtually all the printers from OC Canon. So it's interesting to be able to do this, because, for instance, you could use this as follows: that whenever a change is being made to the software, we can check whether we still have the same state machine. And maybe we do want to change the state machine, but usually often we don't. And so then you can use model learning for regression testing. Ideally, industry would like to use these models to generate implementations automatically, but I think that's still quite challenging. So in these case studies with industry, what we discovered is that sort of learning models is not the hard part. The hard part is this equivalence oracle. And so when we have constructed a model, we need to figure out whether this model actually describes what the implementation does using conformance testing. And we really hit the limits of conformance testing theory. And actually we, as part of our research, we had to improve some of the well-known conformance testing algorithms to be able to deal with this case study. And so here you see a visual representation of the state machine for the OC controller, which has several thousand states. I think the initial state is somewhere up to the right, and then after a sequence of transition you move to this body, and then you see a few sort of tentacles coming out, and these are very specific sequences of events, and if those occur, the system ends up in a deadlock. And engineers from OC have confirmed that indeed there are deadlocks. These sequences of inputs are so weird that when this happens, you have to power off your printer and restart it again. We also looked at software from Philips Healthcare. So what we try to do is to support the development of a refactoring of a legacy component. So how did this work? There was one sort of legacy implementation, and then someone at Philips sort of developed an alternative implementation. But you want to be sure that the new and the old implementations exhibit the same behavior. Or at least if there are differences, you want to understand them. So what we did is we learned models for both of them. And then we checked whether these automata were equivalent. And well, if they are not equivalent, it could be that that there is a difference between the software, but it could also be that the models were still not right. So first we try to reproduce the counterexample on the implementations. And if we can do that, then we know that there is a difference in the implementations. And then it can be that when we see a difference, it can be that we say, well, this old legacy software actually was incorrect, and we've been using it for 30 years, but it didn't work, at least in this specific case. And so then we choose to keep the change in the refactoring, but otherwise maybe we want to change our refactoring. So this approach really helped us to find a couple of problems in the refactored implementation. Okay, so there are many implementations, many applications people envisage for this type of technique. And so when you've learned a model of a legacy component, what you could also do is sort of use it as part of a monitor, which sort of checks what the refactored implementation is doing. And if the refactored implementation is doing some strange things, then you can sound an alarm, and then maybe you need to change something. Okay. We applied software and model learning also at ASML. There, these huge twin scan machines have lots of control software embedded into them, and so lots of this is legacy software, and so they are thinking about how they can refactor it and how there may be model-based techniques and model learning could use. And so they gave us the challenge. They said, okay, we have hundreds of interface models, which are basically state machines, and will you be able to learn those from legacy software? And so this was a challenge we took up, and if actually part of it was used for an international competition on model learning. And so here you see some pictures. So there are hundreds of models, and using model learning, we were able to learn some of them, but some turned out to be too complicated. And so here on the x-axis, you see the number of inputs on an exponential scale, and on the y-axis, the number of states in the Mealy machine. And so if you have too many states or too many inputs, then learning becomes difficult. But this is, of course, a wonderful challenge for academic research to try to sort of make more of these points green. And actually, a powerful technique which has been used is to use logs of these software components, because using these logs, you can check whether your hypothesis models are correct, and then using that generate you have counterexamples, and that will help you to improve your models. So I think since this picture was published a few years ago, the green area has really expanded. Okay, so we have set up a website where we sort of collect all these benchmarks for models we have learned, state machines we've learned, because I think that can help to improve algorithms in this area to advance the field. So we support quite a number of different models types. I won't go into it, but deterministic finite automata with Moore machines, Mealy machines, interface automata, register automata. What's interesting is that many of these models are not that big. So here, for a number of benchmarks, and it's maybe a bit hard to read, we see the number of states, the number of inputs and outputs. And so the models are pretty small, often just a few dozen states. And that is because we carefully selected the appropriate level of abstraction at which we consider these systems. And so that was built into the learning, so to say, and that led to rather small models. Okay, there's a few slides which I think I will skip. Let me discuss this. So if we really want to deal with legacy software, we need to be able to deal with the data. So even if you have control software, there are data parameters which occur as inputs and outputs of events. And these data parameters are important. They influence the control. So we can describe this using extended finite state machines. So these are automata where you have a finite number of states. But then there are events which are parameterized by data symbols. And then if a data symbol arrives, for instance, in this transition from L0 to L1, if we push a new data symbol on some stack, then this data symbol will be stored in some register. So these are called register automata, and people have been looking at methods to learn these type of register automata, because then things would scale. So there are a couple of tools which have been proposed by University of Dortmund, University of Uppsala, and also by our group, which can handle limited data types. So our tool actually can only handle sort of integers and the equality predicate, which is very limited. But this is a challenging problem. Nevertheless, using these tools, some nice case studies have been performed. So one of my students, together with Dortmund, succeeded to learn a state machine for part of the TCP protocol. So this is an extended finite state machine, a register machine, where you have actions that are parameterized and guards on predicates, on transitions and updates and so on. And using this state machine, they found a serious bug in the Linux implementation of TCP. Okay, so black box learning has limitations. It is a very effective bug finding technique, what I described. I mean, you give a protocol to a student, you give the student 2 months and you have bugs in the implementation. But if you want to scale it to, say, complex control software, there are some problems. And so what we are currently working on is that we say, well, why would we restrict attention to black box systems? So in some applications, you have no choice, right? So if you want to learn models of some devices, then, well, the manufacturer simply won't give you access to the code or to the implementation. So you have to operate in a black box manner. And if you can learn a model by just black box techniques, that's better, right? You make no assumptions about the implementation. But then if you have scalability problems and you cannot learn, then why not look at the code if in situations where it's available? And especially, for instance, in the case of industrial legacy software, there is code available. So we are looking at that. And so, for instance, one technique we have been using is looking at fuzzing tools. So there are some very powerful fuzzing tools which have been developed by security researchers, which basically sort of try lots of different inputs for a piece of software. And then they look in the executable whether all the branches that occur in the executable are actually hit. And so using some clever machine learning and genetic programming type algorithms, they succeed to hit many branches in the executable. And so that gives us really interesting counterexamples that we can use in model learning. So that is one technique we have applied. Another technique we are currently working on is called Taint Analysis. And so the metaphor is that of an observer of sort of a colony of ants who may just look at the outside to what's happening, and he can see some ants entering, but he doesn't know what happens, and then maybe ants come out, but are these the same ants and whatever. So then what you could do is you could taint the end. You could, for instance, paint an end with some type of paint, which has the property that if this end touches another end, that end also gets colored. And then if you see a colored end coming out of the colony, you know that there has been sort of a chain of contacts. And we do the same thing, can do the same thing with code. And so there's this area of taint analysis where basically you instrument code to track what happens to input values. And so then when an output value occurs, you know that, okay, this is the sum of the third input and the fifth input, that type of thing. And we've been using an existing tool developed by the group of Andreas Zeller, which contained Python. And so this tells us exactly that, okay, at this stage during the execution, the third input was compared with the fourth input, and it was the result was there not equal, and therefore you took this subsequent branch. So we have applied this, and that gives us an exponential gain in learning, and so it's really very promising. Which in a sense is not so surprising because there's extra information on the table, right? We know all the constraints on the input and output parameters and the tests that occur. I won't sort of go in detail through this case study. Maybe mention there's one instructive example. So using tainting, we are able to learn combination lock automata. So a combination lock automaton is sort of an automaton which, if a specific combination of inputs occurs, jumps to a certain state, just like the combination lock on your bike. If you first have a 4 and then a 5 and then a 6 and then a 7, then and only then you jump to some special state where you have access to certain resources, for instance. And using black box learning, it's of course very difficult, if not impossible, to learn these type of behaviors because you have to try all the combinations. But if we have white box systems, then we just see what are the tests that are being performed. So we can sort of look inside the lock. Okay, conclusions. I need to wind up. I think automata learning is emerging as an effective bug finding technique. And we see more and more applications. Many software engineers use it. But there's still a lot of work that needs to be done. And in fact, in particular to make this gray box learning techniques useful in practice, that's still a major challenge. Okay, and yeah, the main application domain we are targeting is legacy software because there's so much legacy software. So if we can do something there, that immediately has many potential applications. Okay, that was my talk. Thank you.
Thank you, Frits, for this fascinating talk. So are there any questions from the audience?
Well, if nobody has
yes. Yes, I have a question. Thanks for the nice presentation, Frits. I was not. It's nice to see this methods to test. Can it also be used by hackers to find, let's say, possibilities to hack in the protocols? It seems to be also something that they could use.
Yeah, so in fact, that is a very good question. And so, you know, when I started in computer science, I had the naive conviction that computers would make the world a better place, right? They make everything more efficient and they solve problems and so on. But yeah, you're right. I mean, this technique can be used by hackers. And so fuzzing, sort of trying arbitrary inputs to see whether you can break some protocol is a standard technique. And basically what we do is intelligent type of fuzzing. So whereas you have a random monkey who just tries any symbol and see what happens, we also try all the combinations, but in a systematic way.
Yes.
And so this is sort of a concern, but yeah, as many of these techniques, they, on the one hand, they allow you to make systems safer, and there are clear guidelines which come out of our research on how you should design protocols to avoid these type of stupid mistakes and vulnerabilities. But yes, on the other hand, also the bad guys may use the technique.
Yeah, thanks. Clear. Thanks a lot.
Any other questions? Mariella, I thought you also had a question.
Sure, if nobody else has a question, but if it,
Well,
I have lots of opportunities to ask questions to Frits.
okay. So I have a question actually, if no one else has a question. So you mentioned that it's an excellent technique to identify system bugs or bug failures. But is it also possible to use this technique to predict failures?
Yeah, no, but of course from predictive maintenance.
No, exactly.
That is, no, so at some point we have constructed an hypothesis which sort of embodies our understanding of the behavior thus far. We can analyze. We have this model in our hand. We can fully explore it and point out at bugs and say, well, this and this and this desired properties don't hold. Then, but yeah, does that mean that you can predict failures? Well, I mean, if you have a distribution on the inputs, then maybe you can indeed sort of show that there is a mistake in your system which hasn't manifested itself, but which is there in the model. You've seen it. And then you can predict that with a certain likelihood that should occur the next 5 years or so, right? But you have already found the bug, and so if in the case of a software system, then typically the best thing you can do is fix it, right? So in that sense, the application type of applications I'm looking at is different from the applications you are looking at, where maybe you will not immediately replace a part, but where you will say, well, depending on our analysis, we need to replace it 1 year from now in order to keep the probability for failure low.
Yeah.
But yeah, of course, there are also standard violations which we discovered, which are and people don't modify the code because they say it's just too unlikely that this will happen. And that's a typical response when we find a bug.
Okay, thank you. Any other questions?
Yes, I have a question, if I may. I was thinking a bit away from finding bugs in software. This automata learning, it applies to deterministic systems, right? But I was wondering if this is applied to things outside of software. Often you have non-deterministic processes, and then I was thinking in how much is this an equivalence of trying to find the parameters in a hidden Markov model, for example? Are there similarities?
Yeah, so that's a very good question. So actually, often in our research, we have to deal with non-determinism.
Exactly.
Right, because real systems often behave in a non-deterministic fashion. But it's interesting that sometimes you have a non-deterministic system with a deterministic abstraction, and sometimes you have a deterministic system with a non-deterministic abstraction. So by abstracting, you can sort of often change things a bit. But then, yeah, sure, we try to extend our work to non-deterministic systems as well. And so for next week, actually, there will be a PhD student who has also been collaborating with Ms. Marielle, who will defend her thesis on sort of testing of non-deterministic systems. And that will be a key step towards also having learning algorithms, testing and learning on two sides of the same coin. And then, sure, there is a link with Markov chains. So also in the case of Markov processes, Markov decision processes, people have been looking at learning algorithms. And then you can sort of exploit the probabilistic nature of these models and the behaviors you're studying. So there's a whole range of papers dealing with learning algorithms for hidden Markov chains, MDPs, and so on. And sure, that's quite related to what we are doing.
Yeah, sounds very interesting.
Yeah, it is.
Thanks.
So I think this concludes this talk and this session. Thank you, Frits, for this fascinating talk. Concerning this talk, I think in two weeks there's another talk. I think I'm there. I'm the presenter. So hope to see you soon then. Thanks,
Okay.
Frits.
Thank you. It was my pleasure to give this talk.
Okay. Thank you. Bye bye.
Thank you.
Bye bye.
Bye bye.